All right, so let's look at some more examples for balancing chemical equations. We've already done a couple of these. Let's remind ourselves of our three rules. Equations must identify all substances involved in the reaction and should not include anything that is not involved. Well, these example problems, these are all doing this step for us. They're telling us the substances that are involved in the reaction, and they're not including anything that's irrelevant. So for these example problems, step one is not really too much to worry about. It's already been done for us. Step two, however, the chemical composition of each substance must be shown. That we are going to have to take care of because, and I'm going to start with the second problem here because it's actually a little bit simpler than the first one, and I think you'll see why once we get the first one finished. So I'm going to start with this problem. We know the names of these compounds, but we don't know necessarily yet the chemical composition in terms of the atoms and the number of atoms involved in each. So we have to do this step by ourselves. So if we're told that there's iron, well, that's the elemental symbol for iron is Fe. And iron is a metal, so it does just exist as an individual element in nature. I don't need Fe2 or some other polyatomic form of iron here. Chlorine, on the other hand, is diatomic, okay? And again, this is just something you have to remember. All of the halogens, chlorine, fluorine, iodine, bromine, they all, like oxygen, they will combine with each other and they won't exist as actual in their elemental form in nature. So chlorine, when they're talking about chlorine combining with iron here, it's diatomic chlorine, it's Cl2, okay? And it's in, the G just means it's in gaseous form, which is the natural room temperature form for chlorine anyway. So nothing special about that. And when I react these two elements, okay, when they combine, I get iron chloride. And this is iron 3 chloride. So remember what this 3 means, okay, in the Stock system. This 3 is telling us that the iron ion, okay, the metal ion here, it has a +3 charge. So it's Fe 3 plus, excuse me, not +3, 3 plus. Chloride is chlorine as an ion, and chlorine is normally going to be, if it's just a single chlorine ion, then it's going to have a -1 charge. So we have a +3 and a -1. So iron 3 chloride has the formula, again, we just crisscross the oxidation numbers, Fe1 Cl3. And that's how I get these to add to 0 in this case. Okay, so we've taken care of step 2. The chemical composition of each substance is now shown. Okay, finally, and this is usually the trickiest part, equations must account for all atoms involved in the reaction. In other words, we have to balance the chemical equation to make sure that the same number of each type of element is present on both sides. Okay, so here on the side of the reactants, I have 1 iron and 2 chlorine. And on the product side, we have 1 iron, but 3 chlorine. Okay, so the ions are balanced. And what that means is I want, since iron is only coming from these two compounds, one on each side, I want this ratio of the number of this iron compound, which is not a compound in fact here, of the iron atoms, to be equal to the number of molecules or units of this compound. That's how I keep this 1-to-1 ratio. Okay, that's how I keep the balance between those two. The problem here is the chlorine. The chlorine is not balanced. I have Cl2 versus Cl3. So I need to multiply one of these by something that's going to balance this out. If I multiply chlorine by 3/2 on this side, okay, 3/2 times 2 is just 3. Then I will have 3 chlorines over here. So I can put a 3/2 as my coefficient on this diatomic chlorine, and that will balance the chlorines for me. And I haven't changed the number of irons. Okay, so now I have balance. And again, just to be sure, I can go through and I can recount 1 iron, 3 chlorines, 1 iron, 3 chlorines. Okay, it's balanced. But I can't in reality have 3 halves of 2 chlorine atoms. Okay, that's I can't have 3 halves of these. I have to have whole numbers here for all of my coefficients. All right, so just like with the empirical formulas, when we're balancing equations, we must reduce the coefficients, just like with the empirical formulas, to the simplest whole number ratio. And 3/2 is not a whole number yet. Okay, so even though we have balance, this is not good enough because this is not really possible. I can't have the 3 halves of one of these. I can only have 3 of these or 2 of these or some other number. So to eliminate a fraction like this, again, just like with the empirical formulas, we're going to multiply by, well, essentially by the denominator here to eliminate this fraction. But when I do that, to keep the ratio between everything and to keep the balance, I have to multiply everything by that factor. So if I multiply this by 2, it will remove the fraction, but I have to then multiply everything by 2. Okay, which is going to give me the following chemical equation. 2 iron plus 3 diatomic chlorines yields 2 iron 3 chloride. Okay, and just to be sure, I'm going to recount, I'm going to double check to make sure that I still have balance here. But now I have a simple ratio, this ratio of 2 to 3 to 2. These are not divisible by anything further common between them. And they are all whole numbers, so I'm good there at least. But we're going to double check for balance. Should be fine. Okay, we didn't break any rules, but we're just going to make sure. So I have 2 irons here now. 6 chlorine. 3 times 2. 2 irons here, 6 chlorine, 2 times 3. Okay, so it's still balanced. All right, so this is the balanced final form of the chemical equation that actually describes the reaction. Okay, this reaction can only occur if I have 2 iron atoms, 3 diatomic chlorine atoms, and those will combine to give me 2 units of iron chloride. All right, now let's come up and look at the first one, which looks like it might be simpler, but in fact is not. Nitrogen monoxide plus oxygen combines to create nitrogen dioxide. Okay, again, be careful. I mentioned this in the last video. When you have oxygen in a chemical equation, it is almost always, well, pretty much in effect, it is always going to be O2. Okay, this is true for many reactions, any oxidation reaction like rusting that involves oxygen combining with something, or combustion. Okay, so burning things, anytime I burn something, that's a chemical reaction and it requires oxygen to combine with something else, okay, to oxidize things. That's always going to be O2 in those types of situations. So I've already taken a step ahead here. I've given the chemical composition of each of these. Nitrogen monoxide means 1 nitrogen and 1 oxygen. Oxygen is diatomic, O2. Nitrogen dioxide is 1 nitrogen and 2 oxygens. All right, now I'm going to run into a little problem here when I try to balance this. So I have 1 nitrogen on this side, 1 nitrogen on this side, 3 oxygens from the reactants, and 2 oxygens from the products. Okay, there's not a simple whole number multiplier here between the 3 and the 2 that will allow me to equalize this. Okay, I'm going to have to multiply one of these by a fraction. But it's going to matter which of these I pick to multiply by that fraction here, because, and this is going to be the case in all these in a lot of these reactions involving oxygen. I shouldn't say all, but much of the time when you have oxygen involved in the reaction, because it's O2, and then you have oxygen being a common element, it's also in some other compound. This ratio between them of 2 to 1, okay, or of having an odd number, this is really where you run into the problem, is when you have an odd number of oxygens on one side and an even number on the other, you're going to need to work with fractions in order to balance this. And it can be tricky because if you try to balance it using the wrong compound, you won't be able to. Okay, you won't be able to complete the balancing process. So let's do it wrong first so you can see why this is an issue or how we run into troubles here. So I'm thinking, okay, I have 3 oxygens here and maybe 2 oxygens here. So how could I get these to be equal? Well, I could multiply this one by 3 over 2. Or I could multiply this one by 2 over 3. I'm just going to choose arbitrarily here to do this one by 2 over 3. Okay, so I'm going to change the coefficient on this compound to 2 over 3. But this 2/3 is being applied to all 3 oxygens, and only one of those is coming from here. So I actually have to do this to both of these, to this whole side, to all of the oxygens involved for this to even begin to work. So if I do that, then I have 2/3 times 3 is 2 oxygens. So now I have 2 oxygens on this side and 2 oxygens on this side. But the problem is, again, the reason I don't want to choose this compound to try to change the coefficient of, at least at first, is that this also involves nitrogen. This includes another element. And so when I multiply by 2/3 here, I'm not only changing the number of oxygens, but I'm also changing the number of nitrogens. And now I don't have balance between the nitrogens. And what you'll find if you continue to try to do this with the wrong compound is that you'll continue to have this oscillating problem of, okay, now I balance the nitrogens, but now the oxygens are unbalanced. Or now I balance the oxygens, but the nitrogens are unbalanced. And if you just keep multiplying by fractions in a series of steps like this, you'll get this vicious circle that never actually resolves, and you can never break out of. So what's the correct way to see this in order to get balance? Well, it's to look at the other compound that's involved, the oxygen, and to think about changing the coefficient on that instead. So let's back up and go back to the beginning of the problem. So I have 1 nitrogen, 3 oxygen here, 1 nitrogen, 2 oxygen on this side. Is there a way I can change the coefficient on this only? Because I don't really want to change the coefficient on this, because I have what I want here for the nitrogen. 1 nitrogen from this, 1 nitrogen on the other side. I don't really want to change the numbers on that because that would throw this nitrogen balance off. But I just want to change the balance on the oxygen. And well, this element, or excuse me, this compound is only involving oxygen. So that's what I want to work with really here. Is there a multiplier I can put on this that will change the number of oxygens over here to 2 instead of 3? Well, right now I have 2 here and 1 here. But if I cut this in half, so if I make my multiplier on this a 1/2, then I would have 1 oxygen from this, 1 oxygen from this, which would be 2 oxygens total, which would give me the 2 oxygens on this side that I need. And this is what you're going to see a lot with these reactions involving oxygen or other diatomic elements, is this fraction of something over 2. Usually 1 over 2, or usually you can reduce it to a 1/2. Okay, so that's going to give me balance. But again, now I have this problem. I don't have whole numbers, but that's easier to fix, okay, than going through this cycle of playing with fractions and trying to get things to resolve, and ultimately that will be very difficult. All I have to do to get rid of this problem of the fraction is multiply by everything by some factor that will reduce it. So if I multiply all of this by 2, then I get this form of the equation. 2 nitrogen monoxide plus 2 times 1/2 is 1 oxygen molecule will yield 2 nitrogen dioxide molecules. And again, I'm just going to check for balance. That is my final form, but I'm just going to double check. 2 nitrogens, 2 nitrogens, 4 oxygens from this side, and 2 times 2 is 4 oxygens from this side. So I've achieved the balance that I want. This is the final form, the balanced form of this chemical equation. Okay, another example. And in fact, this is a combustion reaction because we're talking about something burning in oxygen. So ethane which is related to methane and other gases, carbon-based gases. You wouldn't expect you to know the formula for this, so I would just give you the formula in this case. So we know that ethane is C2H6, burns in oxygen, producing carbon dioxide and water. Okay, look for these types of keywords. Producing here means that these things are going to be the products, so they're going to be on the right side of your chemical equation, and then the things that are producing those are the reactants. They're going to be on the left side. So we're going to have ethane, C2H6, plus oxygen gas, again is O2, not O. And when I have energy applied to that, it's going to burn the ethane, and we're going to get the oxygen is going to combine with it in some way to produce carbon dioxide, CO2, and water, H2O. Okay, so I've come up with the composition. Now I want to check for balance. So I have 2 carbons here, 1 carbon here. I have 6 hydrogen and 2 hydrogen. I have 2 oxygen and 3 oxygen. Okay, I just take this one element at a time. I can start by balancing the carbon, for example. If I had 2 of these, then I would have 2 carbons on this side and 2 carbons on this side. So we're going to at least temporarily, again, this might not be the final coefficient that we want here, but we're going to, for now, just to balance the carbon, we're going to change it to a 2. Okay, now I have to recount. I have to recalculate my numbers. I changed not only the number of carbons here to 2, so I have 2 carbons and 2 carbons, that's good, but I also changed the number of oxygens. So now I have 2, 4, and an extra. So now this is 5 oxygens instead of 3. Okay, and I didn't affect the number of hydrogen at all. So I'm still trying to balance hydrogen. Well, I could do that if I had 3 times as much hydrogen here. So if I had 3 water molecules instead of 1, that would effectively triple the number of hydrogens that I have. So if I change that coefficient to 3, I'm going to have now 6 hydrogens, but again, I've changed the number of oxygen now. So now I have to recount my oxygen yet again. And now I have 4 oxygens plus 3 oxygens. So now I have 7 oxygen atoms on this side. Okay, I've balanced my carbons, I've balanced my hydrogens, but my oxygen numbers are not yet balanced. Okay, and again, you'll notice I have a similar problem to the last situation. I have an odd number of oxygens here and an even number of oxygens here, which means we're going to have to use some kind of fractional form of 1/2. And again, it's this oxygen molecule here that I'm going to want to look at. Okay, how do I get this to become 7? Well, I need 7 over 2 of these. That would give me 7 and 7. So I'll just change the coefficient on the oxygen to 7 over 2. Okay, and then theoretically everything should be balanced because I didn't change the number of carbons or hydrogens over here, just oxygen. That was the only thing that wasn't balanced at this point. But now I have this problem again of this is not a whole number. So I multiply everything by 2. And that should give me the following chemical equation, which should hopefully still be balanced. I get 2 ethane, 2 C2H6, 7 oxygen molecules, yielding 4 CO2 and 6 H2O, 6 water molecules. Okay, so again, what this equation is telling us is if I take 2 ethane molecules and 7 oxygen molecules, and I apply energy to that and cause burning to happen, I burn the ethane, it's going to break the ethane down and elements are going to recombine in this form. I'm going to get 4 carbon dioxide and 6 waters as a result of that burning. And in fact, get used to this idea. Every combustion reaction, every time you're burning stuff, you're going to be producing at least carbon dioxide and water. sometimes also some other components, but at least those two. Those are common to pretty much every combustion reaction you can possibly have. Okay, we just double check our numbers to make sure that we still are balanced. 4 carbon on this side, 4 carbon on that side. That's good. Carbon set. 12 hydrogen here, 6 times 2, 12 hydrogen there. We're good. 14 oxygen here, 4 times 2 is 8, plus 6 oxygens from the water is also 14 oxygen, so the number of oxygens is also balanced. So this is indeed the correct balanced form of the equation. Okay, just a couple of other examples to go. Aqueous aluminum nitrate. Okay, again, aqueous means that this compound is dissolved in water. Okay, so aluminum nitrate is, aluminum is usually +3, nitrate is NO3 minus. So I need 3 of those nitrates to balance out with the aluminum. And it's an aqueous solution, okay, which means it's dissolved in water, which actually means that these are uncombined. I have aluminum ions in the water, Al3+, and I have nitrate ions in the water, NO3-, and they're all distributed throughout the water sort of as evenly as possible. But for the purposes of the chemical reaction, we don't actually need to describe it that way, although we're going to see later there is a way to do that. But for now, we're just going to consider it like it's a whole compound. And aqueous sodium carbonate. So sodium carbonate also is an ionic compound. Sodium is +1. Carbonate is CO3 2-. So I need 2 sodium for every carbonate. So that's the formula for sodium carbonate. It's also an aqueous solution. They react to form, so now we're talking about the products, a precipitate of aluminum carbonate. That means the aluminum carbonate is going to be a solid, and it's going to fall out of solution after this reaction occurs. Okay, it's going to rain down as little particles of aluminum carbonate or aluminum carbonate snowflakes. How cute, right? Aluminum again is +3, carbonate is -2. So I crisscross, aluminum carbonate is Al2CO3. And aqueous sodium nitrate. Okay, so this remains dissolved. The sodium nitrate is NaNO3, okay, from +1 and -1 on the nitrate, so 1 of each. And that is still dissolved in the water. So that will not precipitate, just the aluminum carbonate will. So I've taken the word equation and I've changed it into its actual chemical formula for the composition of the elements, but we still don't have, we're going to see we don't have balance. So I count my elements, individual elements on each side. I have 1 aluminum here, 2 aluminum here. I have 3 nitrogen, okay, and no nitrogens from here, so just 3 nitrogen total. On this side, I have 1 nitrogen and no nitrogens from there. I have 9 oxygen from this and another 3 from that. So I have 12 oxygen. And here I have 9 oxygen from this compound and another 3. So I have 12 oxygen again. Okay, so that's nice. The oxygens are already balanced at least. And then I have sodium, 2 sodium versus 1 sodium. And I have 1 carbon versus 3 carbon. Okay, so we have a lot more elements in this example than in some of the other ones. So this is going to be potentially going to be a little bit trickier. But again, we're just going to take 1 element at a time to start. So I need 2 aluminum as a result. So that means I need a couple of aluminum over here, okay, to begin with. So we're going to multiply this by 2. So I'm going to put a coefficient of 2 here. And now I have to recount and recalculate. What does that change? That changes the number of aluminum so that they're balanced, but it also changes the number of nitrogen and the number of oxygens. So now I'm going to have 3 nitrogen times 2. So this is now 6. And I have 9 oxygen times 2. So this is now 18 plus these 3 that I had. So this is actually now 21 oxygen total on this side. Okay, and I didn't change the numbers on the sodium carbonate, so these are going to stay the same for the moment. Okay, that is great. That balances the aluminum, but now some other things have issues. If I had, now I need 6 times as many nitrogen on this side. So if I multiply this by 6, that means I put a 6 here in front of the compound that has nitrogen on the product side. And again, I have to recalculate some things. I now have 6 sodium also. And I have 6 times 3 is 18 oxygen from this, and then 9 oxygen from the aluminum carbonate. So now I have 27 oxygen over here. Okay, so I have 2, 2, 6, 6, but these are still not balanced. Okay, I'm going to hope that the oxygen is going to take care of itself if I play with the sodium and the carbonate, and I'm kind of using my own knowledge a little bit here to cheat like this. I would recommend you to try to do hydrogen and oxygen last in most cases, because those are the ones that are going to give you funny numbers because they're in the most compounds or the more common elements. So I'm going to work on converting this to these. So if I have 3 sodiums on this side now, that gives me 6 total, but I also changed the number of carbon. But I changed the number of carbon to 3, which is good because that's what I wanted on this side. So actually I balanced the carbon at the same time as the sodium. And now I recount my oxygen again as well, since I have now 3 times 3, there's 9 here. And then there were 18 from this. So that's a total of 27. And lo and behold, just that one change actually balanced all 3 of the remaining elements. Okay, so I think this is balanced now. Again, we're going to double check a couple of things. We got to make sure, is this the simplest whole number ratio? 2 to 3 to 1 to 6. Well, if it were just 2 and 3 and 6, we could divide all of these by 2. But this single coefficient of 1 here means that, in fact, this cannot reduce any further. So this is as simple as it gets. The only question is, did we actually balance it? We're going to recount our atoms just to find out. So 2 aluminum here, 2 aluminum on this side. 6 nitrogen here, 6 nitrogen on this side. So far, so good. 9 oxygen times 2 is 18, plus another 9 oxygen from 3 times 3 is 27. 3 times 3 is 9, plus 6 times 3 is 18. 18 plus 9 is 27, so the oxygens are right. I have 3 times 2, 6 sodium here, 6 sodium here, so those are balanced, and then 3 carbon and 3 carbon from this 3 carbonate complex. So everything's balanced. I've done it correctly. This is the balanced form of the chemical equation. Okay, this is not that difficult in theory. There aren't that many rules to follow. Honestly, we only listed 3 of them, or 4 if you want to count simplifying your ratios at the end to the simplest whole number ratio. But it is just one of those things that seems very difficult at first, but takes a little bit of hands-on practice to really get the hang of. And you'll get better at this as you actually have to start working through some of the examples on your own, and you'll start to recognize certain patterns and things that will allow you to do it more quickly. If you have any questions, be sure to let me know. I'll be happy to help you.